speaker will be Sergei Gukov.
Well, thank you very much. So, just like this event, the talk will be about physics. So, I have to say that 50% of the audience will actually know 50% of the talk material, because I tried to prepare the grounds for it last week. In fact, we covered several facts, which I'll mention today, so many of you will recognize similar things, but I thought it would be useful to pool these facts together. Plus, I'll supplement them with new results, and my actual goal is to describe relation between Khovanov homology and A-polynomial, both of which are in the world of topology and are nice topological invariants. So last week we only touched upon it, and basically I prepared the ground for it, but in this talk I'll try to summarize what the relation is and give you a holistic picture of everything. So it will be a little intense, and so I saved time on drawing 10 crossing knots. I decided to do it with slides. If I could show you a movie, I would. So this is the closest to the movie that I have. Don't feel intimidated. Feel free to interrupt me and ask questions, even though this is computer presentation. And anyway, finally, my goal is to cover this recent work done in collaboration with Hiroyuki Fuji, which looks a little uptight, and Piotr Sukovsky, both of whom are on background of these nice Feynman diagrams. Okay, so what? Sorry? Oh, I see. The physics is cut a little bit. Yes, unfortunately, I hope none of my slides. Oh, Fuji Film Company. Oh, he's not related to Fuji Film Company, but I realize the Fuji color, as you realize, is relevant to the talk, because we will be talking a lot about colored something, and then Fuji is the name of my collaborator, so it's all about Fuji color. So, those of you who were here last week know why the joke is or what I'm talking about, but it will be apparent later on anyway. So I'll start repeating basic definitions. So we need the definition of the A-polynomial. That's a classical knot invariant. And more generally, the talk will be about taking topological data of the knot and translating it into data of algebraic curve. So all of this talk is going to be about algebraic curves associated with knots. And that's pretty important because to study knot invariants, we usually use various topological tricks and so on, which are of a completely different nature, either combinatorial or involve heavy algebra. And with algebraic curves, we'll be doing geometry such as algebraic geometry or studying various deformations thereof. So there will be geometry behind knots. That's the slogan, if you wish, or the big word. In the present case, this algebraic curve is defined as a zero locus of a polynomial, and what it is, it's representation variety, which studies maps of the fundamental group of the knot complement into SL to C. And one can work out that if one looks at such homomorphisms, modular conjugation by SL to C, what one gets is algebraic curve, and a polynomial by definition is the defining polynomial for this variety, for this algebraic curve. So that's what it is. That's a definition in a very concrete way. So let me again review the basics. This is the tubular neighborhood of a knot in a three-sphere. So imagine a knot such as Trefoil sitting in a three-sphere. It's shown here by dashed red line. That's the knot K. The whole thing is the tubular neighborhood of the knot K. And in this tubular neighborhood, the boundary sigma is just a torus and has two special curves. One is called longitude. That's the blue curve which goes along the knot. And there is a meridian which has linking number 1 with knot itself. Then, if you're interested in studying representations of the knot group into SL to C, it's convenient to ask ourselves a question. First of all, what about representations of these two elements of pi1, in this case pi1 of the boundary of knot complement, into SL to C? Well, the boundary sigma is just a torus, so it's commutative. Therefore, both holonomies can be diagonalized simultaneously, and we call their eigenvalues to be x and y. So then this is the first approximation to the problem. We analyzed what's happening at the boundary of the knot complement by excising exactly this solid torus from the 3-sphere. So the rest is to analyze the knot group, and that's where interesting stuff comes. For instance, for the trefoil, the knot group is just generated by A and B, obeying this braid relations, ABA equals BAA. Now, our job is to study representation variety of this group, which captures a good deal of information about the knot. And that's what we do. We basically replace A and B by 2x2 matrices and try to represent pi1 of the knot into SL2C. In terms of our meridian and longitude for the trefoil, for instance, generator, which we call M, which is meridian of the knot, is just generator A in this presentation, and longitude is a certain combination of B's and A's. And after doing some algebra, one can find out that this representation of this group is into SL2C when we represent it by 2x2 matrices ends up being a relation among x's and y's, which are zero locus of this polynomial. So let me remind you guys what various terms here are. Here, this polynomial is reducible. It consists of two pieces, and one of the pieces is easy to see. For instance, if you look at representations into Khovanov SL2C, namely if we look at reducible representations, then it basically means that everything here commutes, and well, x's and y's are all diagonal, so M, A, B, and so on are all commutative matrices. In this case, representation of pi1 into something abelian basically says that A squared times B is equal B squared times A. In other words, A equals B. And if A equals B, it means that longitude, which is expressed like so, and is equal to B squared divided by A squared, has to be equal identity. So it actually forces the longitude to be trivial or corresponding holonomy to be identity, and meridian can still be anything. So that's why we get a factor y minus 1. It comes from abelian representations, where instead of representing A's and B's and possibly other generators by 2x2 matrices, we actually look through only at diagonal matrices, basically, where everything commutes. So of course, interesting information is captured in non-abelian nature of this group, and that gives rise to a second factor here in this expression. So this phenomenon, which I just explained in the example, is part of the general story. If we study abelianization of the fundamental group of the knot complement, yes?
Why can you assume that you have upper triangular representation?
Why do I assume?
You seem to assume that you have upper triangular representation.
Which representation? Upper triangular representation. Yes, yes, yes. So, in fact, for most of the time, I can even assume that whatever appears here as stars is just 0 if things are in a general position. So here, what's going on? We're looking at, so sigma, which in this case is a torus, is boundary of the 3-manifold M, which by itself is a knot complement. So just a torus. And then we're studying two things. Pi1 of sigma going into SL2C, and pi1 of M going into SL2C. And in fact, we look at the image of the second variety in the first one. So the first one is simply C star cross C star. So this variety, this space here, space of all such representations mod conjugation, is just C star cross C star modulo Z2, which is the wild group. And the reason it comes about, again, is that the fundamental group of torus is commutative. So that's actually the reason why, if things are generic enough, I can actually diagonalize both, and I would have had here 0, in fact, not just star. So it's not about upper triangular, it's about literally being diagonal. And then if, so the star is introduced only to deal with special cases where x's and y's are equal to 1. So then what may happen is that it may be either diagonal or have a Jordan form. So that's why I put a star here. But if x and y are generic, then I don't even need it. OK, so coming back to this definition, when we study representation of fundamental group of a three-manifold or not complement somewhere, it's convenient to look at abelianization of the fundamental group. And that's, of course, first homology, which for a not complement would be always a copy of Z, would be one-dimensional. And that's what gives rise to this factor y minus 1, which we just saw in a particular example. So the claim is that a polynomial of any knot contains the factor y minus 1. So then I'll give you several other properties of the A polynomial so that those of you who haven't seen it before get a little bit in the habit of practicing or using it. For example, if knot is hyperbolic, and most interesting knots are, then it's known that this non-abelian component or part of the A polynomial is non-trivial, so it does capture some useful information about knots and likewise three manifolds. Now, if knot is in the homology spheres, then A polynomial involves only even powers of x. And just like in my lectures last week, in this talk, I'm going to suppress this extra factors of 2 and just assume that basically replace x squared by x to minimize the powers, the exponents. Then the A polynomial can distinguish mirror knots. So if you switch, for example, from the left-handed trefoil to right-handed trefoil, what it amounts to is flipping x to x inverse. And there is another useful relation that A polynomial has the symmetry that if you try to flip exponent of both x and y, namely replace x by x inverse and y by y inverse, then up to powers of x and y, you get the same polynomial. So these are some of the basic properties. Now, other interesting properties is that the A polynomial has integer coefficients. That's quite interesting, but it's not so surprising if you think about the definition that this is defining polynomial for zero locus of something for this representation variety. Then you can realize it as a GIT quotient, and then you can quickly show that coefficients can only be integer. In fact, there is a lot of meat in these coefficients. So you can try to plot them or study the Newton polygon of the polynomial. For instance, this is example for the figure 8, which is this knot here. That's how reduced Newton polygon looks like. And the statement is that if you look at the coefficients on the border of the Newton polygon, then they define polynomials in a single variable such that all of these polynomials are cyclotomic. So that's a strange, surprising fact, which up to present day has no good general explanation, I would say. Another useful fact, which has been studied a little bit but also cries for much better understanding, is that the slopes of this Newton polygon for a polynomial encode information about incompressible surfaces in M. These are surfaces for which the fundamental group maps injectively into fundamental group of M, and their slope is defined in terms of how this surface intersects the boundary of the knot complement, or looks at from the boundary viewpoint. And this is a very subtle information about knot. Usually it's not so easy to extract these boundary slopes of such incompressible surfaces, but from the A polynomial it's very easy. You just look at the Newton polygon and you read off the slopes of the boundaries. So that's very straightforward, and essentially with little work you get a lot of useful information. Now, what I explained in some of the lectures last week, and I'll try to emphasize this even more today, that this A polynomial, even though it's defined as algebraic variety by complex equation, it should be viewed as a holomorphic Lagrangian submanifold. And in fact, the interesting part of geometry is captured by symplectic geometry of the A polynomial, not so much by its complex or algebraic geometry nature. So in particular, it lives in the space of x's and y's, which are holonomies, eigenvalues of the holonomials along the meridian and longitude. And you can try to quantize this space with the natural symplectic form. I'll show you a little bit more where it comes from. And then you get some interesting wave functions associated to such Lagrangian submanifold. And then, even though I'm not going to discuss this in detail, in some recent work with Dimofte and Hollands, we even showed that many features of the A-polynomial curve, which is algebraic curve, have exactly the right attributes to represent Seiberg-Witten curve for knots and three manifolds, and so on. Now, what does this connection to physics tell you? It tells you that if you start with classical curve, such as zero locus of ax and y, and x's and y's are again eigenvalues of the holonomies along the meridian and longitude, Chern-Simons theory tells you that the problem needs to be quantized in a way where x and y are replaced by operators which do not commute, rather obey this Q commutation relation, and this is the first time where letter Q shows up. Okay? Then quantization also tells you that classical constraint, that solutions to the classical problem are parameterized by algebraic curve, a of x, y equals 0, translates to quantum statement that some wave function is annihilated by this operator. So then, as we discussed last week, and I'll repeat some of it today, this operator relation is actually Q-difference equation, which expresses how colored Johnson variants and their analogs depend on the color. So in the title, I asked about relation of A-polynomial and Khovanov homology. So the relation will be exactly the same, or essentially a categorification of this relation here, where color dependence, or dependence on choice of representation by which the knot is colored, is exactly captured by some algebraic curve. Now, something we didn't discuss last week, but we touched a little bit upon it. See, if you have symplectic structure such as dy over y wedge dx over x, then the corresponding Liouville form, which plays an important role in quantization, is basically primitive of that symplectic form omega. It's log y dx. It turns out that for any closed cycle on a Riemann surface defined by zero locus of A polynomial, integral of this one form over such cycle, any cycle that you want to choose, has to be rational multiple, well, rational number times 2 pi squared. This condition is very important for quantization, for otherwise Chern-Simons theory would not make any sense. And it's very interesting to check that for A polynomials, which sometimes define Riemann surfaces of very high genus could be 100, for example, even for basic pretzel knot, and therefore you have lots of cycles to choose, this condition is always satisfied. So it's a very delicate condition, and it actually knows a lot about these number theoretic aspects that I mentioned in the beginning, that not only coefficients of A polynomial have to be integer, they have to be very special integers. So they have to satisfy certain integrality constraints. And this can be interpreted, on the one hand, as a fact that Riemann surface gives rise to theory which is quantizable, and on the other hand, can be restated in terms of condition in algebraic K-theory. So just to illustrate what it is, suppose you have, so this is the A polynomial where I remove this boring factor y minus 1 for the figure 8 knot. So that's how it looks like. It's very similar to what we discussed last week, and just yet another example. So it's interesting that for this A, the Riemann surface has genus 3. So there are quite a few A cycles and B cycles where I can try to study this condition, evaluate this condition. And if we preserve all of the symmetries that A polynomial has, namely it has to be reciprocal, it has to, its boundaries should define cycloatomic polynomials, namely it should be tempered and so on. So we can preserve all of the symmetries, just change one little thing. I'll change this minus 4 and plus 4, which enter symmetrically, into minus 6 and plus 6. And what's interesting is that this condition is immediately going to fail. So you see it detects a lot of very useful, delicate structure that probably underlies some of the number theoretic properties of the A polynomial, but again, I think that's worth studying further, and so far this has not been really done. Anyway, I want to continue and focus on this operator relation that you get upon quantization. So you start with the classical equation A of xy equals 0, and then quantization turns this into operator relation. Operator relation that's supposed to annihilate wave function of the Chern-Simons theory, and it's known that Chern-Simons theory computes for you John's polynomial or colored John's polynomial or other quantum group invariants. And it's easy to work out that relation between variable x and so-called n-colored John's polynomial, where you have n as a dimension of representation, is such that x is equal q to the n. That follows directly from quantization of Chern-Simons theory. So this is the relation that I'll often use. The classical variable x turns into q to the power n, where n is dimension of a certain representation. Therefore, classical limit is really where q is very small, but in the same time n is very, very large, so that q to the power n is finite. Any questions up to this point? So then, as I say, it's known that Chern-Simons theory computes various quantum group invariants, such as colored John's polynomial, which we're going to discuss next. If you have a knot sitting in a 3-sphere, then path integral of Chern-Simons theory for knot colored, say, in n-dimensional representation of SU2 would produce for you a polynomial in a variable q, which is, by definition, the colored John's polynomial. And let me review that a little bit. If n is equal to 2 little n, then this is just the usual John's polynomial. It can be defined by skein relations, where you iteratively change knot diagram by replacing overcrossing to undercrossing via this relation. If you start with John's polynomial for the unknot, which has 2 terms, then you can compute it for every knot in a nice systematic manner. And that's the example which we discussed last week. That's the John's polynomial of the Trefoil expressed in these variables. Now, the colored Johns, we didn't talk so much about it, but it's exact same analog. It produces polynomial knot invariants, polynomials in Q, for each value of n. And the meaning of it is that it's computing for you quantum group invariant associated with SL2 and its n-dimensional representation. So you have a sequence of polynomials indexed by n, such that each polynomial is a polynomial in variable q. Now, they can be computed in a very simple and systematic manner by using so-called cabling formula, which simply encodes the rules of the TQFT. So the rules are very simple. You have to use essentially 2 of them. That first of all, if you have a knot and decide to color it with a direct sum of representations, then it's basically going to be a sum of polynomials that you associate for each representation R. And also, if you decide to take the tensor power of a given representation, then it's the same as computing the John's polynomial in a simpler representation, but of a more complicated knot. So you can kind of trade complicated representations for complicated topologies. And this is so-called n-cabling of the knot, and it's produced by taking n strands instead of a single strand, following it along the knot, and then closing everything into a single knotted circle. Yeah. These conditions allow us to determine, no, you start with the John's polynomial, but then these conditions help to determine this colored John's. So for n greater than 2, they allow to determine all jn's in terms of j2 or the usual John's. So in fact, that's what I'm trying to illustrate in the next slide. This is really not very mysterious. All these jn's, they're produced as follows. For example, j1 associated with trivial one-dimensional representation of SL2 is always trivial. So for any knot, it's equal to 1. So let's normalize it just like that. Then we already talked about j2. This is the usual John's polynomial, and it could be computed by skein relations. And we had some practice last week how to actually do it. But then that's all we need to know to compute all j3s, j4s, and so on. And the computational rules encode very nicely the simple representation theory of SU2, a very classical theory. So, for example, if you take a two-dimensional representation, which gives rise to the usual Jones polynomial, and take the second tensor power of it, you get one-dimensional and three-dimensional adjoint representation. And reflecting this simple rule and representation theory, you have J3 equal to J of a second cabling of the knot minus identity, and so on and so forth. For example, you can take the third tensor power of a two-dimensional representation, you get two two-dimensional ones and a four-dimensional guy, and as a result, J4 can be expressed in terms of three cabling and K itself. So it's very simple combinatorial rule which allows you to use this cabling formula which I had on a previous slide, and it reflects exactly the structure of how to tensor representations, except that you replace tensor powers of representations by the corresponding cablings of the knot. And again, the idea is very simple. If you want to compute something for high dimensional representation, namely more general Jn, all you have to do, you can always reduce the problem to computing the usual Jones polynomial, but for a more complicated knot, for nth cabling of the knot. That's the idea. Now, this is what's happening. You start with this operator relation, which says that partition function of Chern-Simons theory should be annihilated by a certain operator. And this statement has several consequences. Consequences for the behavior of invariants Jn of Q as functions of Q in the limit where n becomes very large. So this is, as we discussed before, essentially is the classical limit. So first, the statement is that if you analyze asymptotic behavior of this color Jones invariance when n goes to infinity and Q approaches identity, again, that's a classical limit, then this invariance will exhibit exponential growth. And if you keep variable x, which as we discussed before is Q to the n fixed, then the answer will be of the form exponential of 1 over h bar times some function of this parameter x, which is kept fixed in this limit. So this asymptotic behavior is, of course, very suggestive that the right-hand side is semi-classical expansion of some quantum problem. And this quantum problem is nothing but Chern-Simons theory, but with analytically continued gauge group SL2C rather than SU2. In particular, it has something to do with representations into SL2C, just like A-polynomial is supposed to tell us. So that's what I say here, that S0 of x is in fact a classical action of SL2C Chern-Simons theory. And this statement, this asymptotic limit of colored quantum group invariance giving you exponential behavior, in the literature it usually goes by the name of generalized volume conjecture. And the reason for this is that SL2C structures on the knot complement or in one-to-one correspondence with hyperbolic metrics, provided you have some positivity and non-degeneracy conditions. So, therefore, this side of the relation involves classical hyperbolic geometry. It's a classical Chern-Simons action based on SL2C, and is very nice and geometric. This side of the relation is very quantum and involves combinatorial quantum group invariance, things like that, which a priori have nothing to do with classical geometry or hyperbolic geometry of the knot complement. So, yeah?
I mean, this Chern-Simons action usually, I mean, it's an action function where you plug in a connection or something like this. So where is, I mean, how to interpret that?
Right, so we were studying the problem of maps originally from fundamental group of M into SL2C. And again, I'm compressing some information here a little bit more telegraphically, but what I was explaining last week basically is that this space, which I'll call M flat for 3 manifold M with a structure group G, or let me make it SL2C, is exactly the space of solutions to equations, to the flatness equations dA plus A where J equals 0 on the one hand. So that's exactly this algebraic curve defined by the zero locus of the A polynomial that we're discussing. So then it turns out that, so basically you can, every point here corresponds to some class conjugacy class of flat connection. Then if you ask yourself, what is the Chern-Simons action for this gauge connection A? You'll produce something which is exactly what appears here. And I'll tell you yet another way how to write this function as 0 of x in just a moment. But you can view this problem, the original problem that we're discussing, I formulated it as a problem of studying representations of the fundamental group somewhere. But we could have started by studying flat L2C connections. We would produce exactly the same algebraic curve because this is the space here. And then for each point on the curve on this Riemann surface, so this moduli space is given by the zero locus of the A-polynomial, and it looks exactly like this Riemann surface I was showing you. Some interesting algebraic curve and so on. And then you can ask for every point here, what's the Chern-Simons functional? And claim is that that's the guy which appears here. And again, I'll tell a few words about how to compute it in practice. Does it answer your question?
Yes, it does. So it depends only on the x value.
It depends. Well, it actually.
Something x and y.
Correct. So this is a subtle point. So in fact, here I express it as if it depends only on x variable, assuming for simplicity that I can project everything to x plane, for instance, and there is a natural choice of branch. But you're absolutely right. So in fact, it's more precisely, it's function on the curve. So it's not really a function of x. So that's really a good point, but I want to suppress it for now. Now, in practice, this action, Chern-Simons action as 0 of x, can be computed like in any quantum problem by doing p dq integral. So its dependence on the point on the Riemann surface, so that's better drawing of the Riemann surface that I had on the blackboard, can be obtained as follows. You take this one form, which we already saw before. It's log y dx over x. And then we integrate it along a path, open path, which starts at some fixed point and goes to the point of interest, basically. And then statement is that if you want to evaluate the Chern-Simons action as a functional of gauge connection, and all such flat gauge connections are points on this interesting curve, all you have to do is to perform this integral of p dq type integral of log y dx over x along this path. And then the statement that we had before, remember we also had a condition which I called quantizability condition, that was a statement about all possible integrals of the same one form on closed cycles. So that statement was basically saying that when we put S0 here in the exponent, exponentiating the ambiguity will always get something multiple of 2 pi I. That's where it came from. It came from the statement that the action, once put in the exponential, this functional, gives something unambiguous. So that's where that statement came from. Anyhow, concrete way of computing S0, again, is based on looking at the zero locus of A polynomial. That's a nice algebraic curve. It may be of reasonably high genus and so on. And then you just integrate the one form which comes to you from quantization or equivalently from symplectic structure along a path to get function which depends on where you are on this Riemann surface. Now, another statement which is along the same lines and follows from this condition that quantization of this A polynomial curve annihilates partition function of Chern-Simons theory is the statement that since partition function of Chern-Simons theory is nothing but the colored Jones polynomial, you get some operator relation on colored Jones invariance. And this goes by the name of quantum volume conjecture, because here it's important that you don't take any limits. You work with Q deformation of the algebra, where x and y are Q commutative. If you translate what this action of x and y, x hat and y hat, means on colored Jones invariance, you quickly find that x acts as multiplication by q to the n. That's what we already discussed before. We saw this earlier. And then y acts by shifting label n by 1. In particular, from these relations, it's easy to check that they satisfy the desired commutation relation, which is prescribed to you by quantum Chern-Simons theory. So now you take this commutation relation and you turn it into, this quantum operator A hat, and you turn it into useful operator that acts on color-Jones invariance. But first, let me review the example of the Trefoil node, where the classical curve is given by equation y inverse y minus 1 plus times y plus x cubed. So that's what we saw before. It's of degree 2 in variable y. Then its quantization is also going to be of degree 2, so there will be 3 coefficients, alpha, beta, and gamma. But in the quantum world, they get deformed. And the curve no longer factorizes. So alpha, beta, and gamma also become q-dependent if you do this deformation. Now, if we use our dictionary that x is multiplication by q to the n, and y acts by shift on the color-Jones invariant, namely, it increases dimension of representation for the colored not invariant, then the fact that A hat annihilates partition function of Chern-Simons implies that this color-Jones invariant satisfies recursion relation where alpha, beta, and gamma are essentially the coefficients of the recursion relation. So y hat is a shift, and that's why we get this two-step recursion. And essentially, the rule of the thumb is very simple. If your original polynomial, a polynomial whose curve we were analyzing, is of degree d in y, in variable y, you'll get a d-step recursion. That's the basic rule. So you'll have to know d minus 1 previous terms to determine this goal. So that's another way of writing that same relation, that operator A hat acts on color-Jones invariance, gives you 0. And I should point out that in mathematics literature, this version of the volume conjecture is discovered simultaneously by Stavros Garofalidis and is called AJ conjecture. Now, what are the lessons from this? So I'm going to, again, I'm very quickly reviewing some of the important facts which I want to generalize. And if I were to say figuratively what a polynomial is based on this lesson, it encodes representation dependence or color dependence of colored Jones polynomial. So you can view it as a limit shape. Such problems typically involve combinatorial objects where you analyze how things behave in a limit where, for example, number of object grows or combinatorics is supposed to get replaced by classical geometry. So that's what we're doing here. We're studying color-Jones invariants, which are polynomials. They have very discrete structure, very specific coefficients, and their size is growing as n goes to infinity. But they grow to infinity in a very nice controllable way, which is described by algebraic curve. So in that sense, a polynomial is this limit shape. And there is a lot of regularity in coefficients, even though the size is growing and so on. Another way to say it is that this q-difference equation, which we just saw on the previous slide, or recursion relation, can be viewed as a quantum operator whose classical limit is exactly the a polynomial. So from the theory of D modules, or from the viewpoint of such q-difference operators, a polynomial is just characteristic variety for this structure. And what I want to describe next, and this is actually the main point of this talk, is that all of this, which I said to you in a moment ago, can be nicely categorified to a homological statement. So what we saw here is that the quantum group invariants behave in a very specific prescribed way if you change color, so the Jones polynomial. What's more surprising, and I didn't expect this when I started working on this problem, is that homological invariants, not homologies, also exhibit regularity and also exhibit similar behavior where you ask what happens if you send something to infinity. They also can be described by algebraic curves. So that's a surprise. Now, Khovanov homology is categorification of the usual Jones polynomial, and what it does, it assigns to every knot k bigraded homology groups such that Jones polynomial is graded early characteristic of these homology groups. So that's the example of the Trefoil knot. John's polynomial, which can be computed by skein relations, has 4 terms which have coefficients plus minus 1, and they can be viewed as arising from even and odd gradings, homological gradings of Khovanov homology, which modular torsion also has 4 pieces, and there is only one minus sign, which has to do with the fact that this copy of Z, or Q, if we're over rationals, is in homological degree 3. Everything else is in even homological degree, so there are only plus signs. Now, similarly, one can categorify colored Johnson variants, and the corresponding homology groups are labeled by SL2 because we're doing SL2 theory, and n-dimensional representations, Vn. So you get so-called n-colored SL2 knot homology, and you can encode a lot of information about it by constructing the Poincare polynomial, where variable q keeps track of the q grading, and variable t is the new homological grading that we gain in the process of categorification. So, of course, the statement that such groups categorify colored n-colored Johnson variants means that Jn that we discussed before and that can be constructed by cabling formula can be obtained by specializing these Poincare polynomials to variable t equals minus 1. That's the usual process of taking early characteristic. And it's interesting to remark at this point that unlike the colored Johnson variants, homological invariants cannot be constructed by repeating the cabling trick, this cabling formula. It doesn't work, and that's why constructing colored knot homologies is more interesting. In particular, that's why it's not obvious to ask what is the large n dependence of those homological invariants. All right, so what we're going to discuss is more or less the same story for SL2 n-colored knot homology as we did for colored John's polynomial. So one can ask several questions. What happens if I send the dimension of representation by which n is colored to infinity? What happens? Is there any regularity in large n limit? Or are there any recursion relations between Poincare polynomials of knot homologies? So that would be extremely useful. And it turns out that the answer to both questions is yes. And what's interesting that they're also controlled by some algebraic curve, but now it's a certain deformation of the curve that we discussed before. It's a deformation because it now knows about t dependence, this homological grading, which is a new dimension, whole new dimension in the world of homologies. Now, this stuff comes from physics, and very recently, only in the past year, it was basically realized that a polynomial can be deformed, and in fact deformed in 2 different ways. That's what I'll tell you about next. It admits so-called t deformation, which is the same t that we saw on the previous slide and has to do with homological deformation, but it also has a deformation. That's another one, and both of these are certain polynomials which are deforming a polynomial. I'll tell you a lot of properties that come from physics, but I don't know mathematical definition of these deformations. For example, a polynomial has a clear geometric meaning. It was describing representation variety, space of representations of knot group into SL2. I have no idea what it means to introduce variable t or variable a in those geometric terms. But from physics and some other means, I know that this exists, and in fact I'll show you explicit computations of these deformations and make concrete conjectures. But it would be very desirable to actually understand any of these deformations, either t deformation or a deformation, more rigorously or mathematically.
So
yeah.
What do they mean? I mean, you said from physics, but you didn't say.
Yeah, so I'll tell you the answer. I'll tell you the properties of these deformations, and some of the meaning will become clearer. So t deformation has to do with homological deformation. A deformation has to do with generalizing SL2 theory to SLN theory. So, and but it's a very interesting prediction, which again cries out for better theory, just like a polynomial was defined very geometrically and in terms of original data of the knot, one could hope that there is a deformation, or in fact two deformations of such of this structure, which allow you to talk about polynomials which depend on a and t as parameters. So in fact, to emphasize that a and t are parameters, and we still talk about algebraic curves, I put this semicolons in all slots. So finally, there is this combined deformation by a and t, and the diagram commutes in the sense that I'm going to describe later. But again, the point of this whole talk is that a lot of information about knot homologies can be captured by algebraic curves in some surprising way, and it is this A and T deformed algebraic curves which capture information about Khovanov homology. So as I promised you, here is what the answer looks like for T deformation. What you can see here is some complicated expression which leaves this polynomial of degree 2, reducible originally, as a second degree polynomial in y, but it introduces a bunch of t's in various places and does it in a very strange way. But it's easy to check that if you set t equals -1, you actually reduce to this form. But more, again, this computation comes from physics, and I would love to see some mathematical definition or deformation of the original a polynomial that does the same job. Here is another one. That's the deformation by variable a, and it has the property that if a goes to 1, you also recover the previous curve, and it has roughly the same structure. You see that it makes polynomial irreducible, it makes it much more complicated. Other than that, I honestly see no structure here. So just some random deformation. What's interesting is that this polynomial has been recognized in math literature, and it happens to coincide with so-called augmentation polynomial of knot contact homology that Lenny Ng and collaborators have been studying. So it's again open question whether this is just coincidence or there is some more rigorous story behind it. Finally, if you combine two deformations, a and t, you get even more complicated expression. So you have a polynomial of degree 2 in variable y. It involves x and now involves lots of parameters a and t at various places. So, and various specializations give you the simpler ones. Okay, each of these polynomials can be quantized. The rule is still the same. You have x and y, which are q commuting by this parameter quantum variable q, and therefore they produce for you the recursion relations. Now, if you start with a classical equation for polynomial in x and y, which has a and t as parameters, also by quantization you get a third parameter, q. Now you have lots of them, but anyhow, you produce something of the same form that we saw before. I'm not writing explicit expressions for alpha, beta, and gamma. These are certain rational functions now of a, q, q to the power n, and t. So there are a bunch of parameters. Now, you get a recursion relation, and natural question is, what is this recursion relation for? What is its purpose in life? Okay. So to answer this question, we can do the exercise analogous to baby version of this exercise that we did last week. We can try to solve this recursion relation starting with Pn equals 0 for all n smaller than 1. Take P1 to be 1, very natural choice of boundary conditions, and the result should be polynomial or whatever expression, maybe some function, doesn't have to be polynomial, in a, q, and t. Okay? So we can try to run this recursion relation, for instance, for the Trefoil knot, knowing alpha, beta, and gamma, and see what we get. So the answer turns out to be quite interesting. So this object, or in fact series of objects Pn of a, q, and t, have the following form for the Trefoil. So the starting point is 1, the next guy has 3 terms, the following guy has 9 terms, and so on. They quickly grow on you. But from this complicated formulas, you see several properties. First of all, you see that Pn's are all polynomials, all polynomial expressions in a, q, and t. And secondly, you see that all coefficients here of p's happen to be non-negative. Okay? So this helps a lot to answer what kind of object Pn is. In fact, it's a Poincare polynomial of a triply graded homology theory. Since it involves three variables, a, q, and t, the corresponding homology theory has three gradings, which correspondingly are called A grading, Q grading, and T grading. And it categorifies Homfly polynomial. So something we discussed last week is that Jones polynomial can be deformed in two different ways. First of all, it can be upgraded to Khovanov homology, which gains variable T, roughly speaking, or new grading. Or it could be deformed into Homfly polynomial by introducing variable A. And Homfly polynomial encodes all SLN quantum group invariants associated with a fundamental representation. So then Homfly polynomial, just like Jones, can be also categorified. So we can try to make this diagram commutative and lift it and combine both T deformation and the A deformation in the same way. So what we get in the end is a triply graded homology. Khovanov homology was doubly graded, so if you introduce another parameter A, you get something triply graded. And this is what's called Homfly homology. Its Poincare polynomial is a polynomial in three variables, A, Q, and T. It has non-negative integer coefficients. And in fact, the answer is that all our PNs that we just computed a moment ago are exactly Poincare polynomials of such theory. So in fact, all of these statements, all of these relations between Jones, Khovanov homology, and Homfly polynomial can be made into so-called n-colored versions. And index n appears on each of them. And then the punchline of the story is that you can ask similar questions about n-dependence for any of these objects. What we saw before are this variance of volume conjecture for original Jones polynomial, but the punchline of my talk is that you can ask similar questions about Homfly polynomial or Khovanov homology, or in fact even this sophisticated triply graded homology, which is supposed to be its categorification. So I should say that this arrow here is very delicate. It's trying to reduce Homfly homology, or its Poincare polynomial, which we call Pn, to corresponding doubly graded homology. So reduction along these lines is very simple. It's taking early characteristic. But reduction along these lines is roughly supposed to be specialization to A equals Q squared. And specialization to SL2 from Homfly. It's very straightforward at the polynomial level. And this is indeed correct statement, but it's a little bit more delicate in the world of homologies. So the reason is that in homological world, we deal with vector spaces. And conceptually, you shouldn't expect any kind of simple relation at the level of polynomials. But more concretely, what's happening is that this kind of reduction, if you expect it naively, so here I draw the same diagram, again, forgetting about the colored stuff, just doing it for the usual Homfly homology, who has PA-QT as a Poincare polynomial. So this is the version of the same diagram where we understand more or less all of the relations. For instance, this is quantum SLN group invariant. This is its categorification. Also in a different direction, it can be lifted to so-called Homfly polynomial. And here reduction is supposed to be Q to the n, A equals Q to the n. But the relation among homologies cannot be that simple, and there is a very simple way to see why it cannot. For instance, if we look at SL1 theory, which corresponds to n equals 1, all polynomial and homological invariants of SL1 are supposed to be boring and trivial. And indeed, if you look at Homfly polynomial and set A equals to Q, which is what you get for n equals 1, indeed, Homfly polynomial reduces just to identity if you properly normalize it. And the way it happens is because all other terms are naturally paired up. So you can always write Homfly polynomial of every knot in the form constant term plus something, which I denote as q quotient, multiplied by this expression. So if you set a equals q, you kill everything, all the interesting stuff. This can never happen at homological level because, or for Poincare polynomials, because all coefficients are positive. So there are no cancellations. They simply cannot happen. And there is no way you can reduce from more complicated expression to simpler one by substitution. There are no minus signs to help you. So it is, however, true that this relation has a natural deformation. What you get is that minus sign here becomes factor t to the minus 1. So there is indeed some structure in the homology. So all terms are still paired up. And the way you're supposed to interpret the relation between corresponding Poincare polynomials of, say, Homfli homology and Khovanov homology is that some terms are paired up and killed by suitable differentials. So this is the structure that we uncovered with Dunfeld and Rasmussen. We were basically studying this diagram and its consistency, and what we found is that the horizontal arrows correspond to setting t equals -1, and there is no subtlety here. This link is also very simple and just substitution, but this link here involves a very interesting homological algebra associated to whole collection of differentials that we call Dn. And if you're interested in specializing from triply graded theory to SLN theory, you're supposed to take your original homology as a complex and start acting on it with differentials Dn, so that resulting homology is the smaller answer you're looking for. So, for instance, that's how it looks like for 8 crossing knot. It's a pretty big theory, and there are lots of interesting differentials that you have here. So some of these arrows correspond to canceling differentials I described. Some of them correspond to differentials that take you from triply graded theory to Khovanov homology. Now, last week I mentioned to you guys examples of knots, the pair 5 crossing knot and 10 crossing knot, which have the same Jones polynomial, the same Alexander polynomial, in fact, the same Homfli polynomial. So now is the time to show why homology is useful and really stronger than polynomial invariance. Part of the reason is that while all polynomials for these guys are the same, homologies are different. So what I'm picturing here are corresponding Homfli homologies for 5-1 knot, drawn here, and 10-132 knot, drawn here. And they simply have different dimensions. So what's shown here in the picture is that A degree is plotted vertically, Q degree horizontally, and number next to each dot or generator in the homology is the T degree. So you see, if you set T equals -1, for example, these guys, they appear in different T degrees, and you get 0. So at the level of Homfli, this disappears. 2 and 3 also disappear. These pairs of dots disappear if you specialize to T equals -1, because you have in the same A and Q degree 2 generators which have weight T squared and T cubed, and of course they disappear if T is -1. And in the middle you get only 1 term left out of the 3 guys. So it's clear why, for instance, from these pictures, why Homfli polynomials happen to coincide. But in the same time, homology, as the diagrams illustrate, are really different. So another even more impressive example which shows why we're doing all this is that many of the polynomial knot invariants, even the colored ones that we discussed, such as Jones, Alexander, and Homfli, don't distinguish operation of mutation. Mutation is simply drawing a knot, drawing 3-dimensional ball, which has 2 ingoing and 2 outgoing points, strands, and rotating it 180 degrees. So this is the famous pair of Kinoshita, Terasaki, and Conway knots, which are related by such operation of knot mutation. And what's interesting is that, again, all polynomial invariants that we discussed so far are completely blind to this mutation, whereas homological invariants detect the difference between these 2 knots. Now, in the remaining couple of minutes, I want to show you that these differentials which we encountered not only are a necessity that we forced upon in homological world, but they actually help us to explain the origin of some of these recursion relations. Indeed, if you compare how, say, homology for n equals 2, little n, this is color, so it's a symmetric, second symmetric representation, compares to homology for the fundamental representation, which I label by Young tableaus. Here I'm using the Schur-Well duality. So this is the answer for triply graded homologies in the same set of notations where each point represents a generator. So Homfly homology of the trefoil is three-dimensional, and we worked with it last week quite a bit. This is the answer for S2 colored homology of the trefoil. It's 9-dimensional. Now, first thing that I want to stress and illustrate by this diagram is that this smaller homology for smaller color or smaller representation is embedded in a bigger representation. So if you know answer for the homology associated to larger representation, you can always find smaller representations inside of it. So in particular, what happens here is that there are generators such as this guy, and let's see, this guy, which have to go in the corresponding generators of the usual colored homology. And then what you notice from the picture very clearly is that what remains, there are some grading shifts and so on, but what remains is always a combination of terms which come in pairs. And we have already seen this before. And anything that comes in pairs, you immediately should interpret as something that's killed by a suitable differential. So the statement is that, just like we did before when we discussed specialization, the relation between colored and uncolored Homfly homology is that if you take cohomology with respect to certain differential, I call it color differential, you obtain the answer for the smaller representation. So that's the idea. That's what it looks like, and at the level of Poincare polynomials, it gives rise to relations similar to what I showed you before, where the smaller answer sits as part of the big one, plus there are some number of terms paired up by these differentials. Now, this kind of relation is example of a more general relation between colored and uncolored Poincare polynomials, and roughly speaking, what's happening is that these color differentials, they act by removing boxes from the Young tableau, or taking you from bigger representations to smaller representations. And this is kind of similar to recursion relations that we saw earlier. Everything I described goes verbatim if I replace 2 boxes with n boxes. Then you basically go in the process of removing 1 box at a time, going to smaller and smaller representations. And this is now becoming to look really like color dependence of homological knot invariance, the question that we discussed earlier. So there is an order in this color dependence. It's not arbitrary, it's very systematic. And previously we saw this behavior associated with quantization of some moduli spaces and so on. Here it appears in a slightly different flavor. It appears as a consequence of this homological algebra or differentials acting on knot invariance. So in fact, this could be viewed as precursion relations, as precursors of these recursion relations that we discussed earlier. So this type of behavior eventually gives rise to some operator which, acting on a sequence of Poincare polynomials labeled by n, gives you 0 that annihilates such a sequence. So therefore, it provides a nice link between homological algebra of such differentials on the one side and quantization / deformation of these moduli spaces on the other side. So I guess I want to finish at this point. In what generality?
And have you defined the three-variable polynomial, PPAQ?
So the definition exists for, the question was, in what generality this P polynomial, right? Poincare polynomial of Homfly homology was defined. So there is a definition by Khovanov and Rosansky for n equals 1, so for fundamental representation. And unfortunately, it's very uncomputable. So that's why much of this is very useful testing ground for general theory, which exists. So there is a definition, and there are cases where it can be computed that are essentially limited to Trefoil, which I showed you here, and where one can check that the answer is correct, and maybe figure 8 not, but that's more or less it. So unfortunately, it's also somewhat geometric, the definition, so it doesn't allow to do any computations. But then for PN, the story is even worse. So there are definitions, but there are no computations whatsoever except for unknot. So unfortunately, I hope that since they are mathematically well defined, it means that someday we'll learn how to actually do computations with them. And that's why I'm willing to go openly in public and say, here is the proposal. That's what physics tells you the answer should be. And it's, of course, a lot of fun to see that it's either correct or incorrect. It's either yes or no. And I'm willing to bet money on this. But then the structure of these colored invariants, PNs, is controlled by A. This involves also this Q and T and A deformation. And that has not been mathematically defined, so that's exactly what I was trying to emphasize. I don't know the deformations of the A-polynomial which give the answer. So
you wrote down some examples.
Yes.
Have some idea how.
Well, again, they come from physics, and unfortunately, in this case, they come from supersymmetric physics. So it's not Chern-Simons theory. It's some dual, complicated system. So this system allows to compute such polynomials, allows to define them in a different way, but it's very different from Chern-Simons, unfortunately. So that's why I'm asking mathematicians to explore the connection. As I say, in one case, it seems that augmentation polynomial of not contact homology is a good candidate for one of the deformations, but that's only one deformation.